for all the people that had to come here on Sunday. But we're going to do some neat stuff today, so I hope it's going to be worthwhile. I wanted to talk about, well, what I'm going to lead to is scaling. Remember when we did two-dimensional matching and we said we want to find someone in different sizes as well. But scaling is a hard topic, and there were some pretty intricate results. So we're not going to go all the way to the end. And we are going to need some previous tools in order to be able to do even the first type of scaling that there is. And so that's why I'm going to start with parameterized matching, because it will help us later on with scaling. And it's a cute problem in and of itself. So what's the problem of parameterized matching? The problem was defined for the first time by Brenda Baker. Brenda Baker in the 1990s. Brenda Baker used to work for AT&T research labs. And of course, that's a research labs from a telephone company. So they were also concerned with problems that arose from telephony. Now, if you saw old movies of people calling on the telephone, they had these phones where there was you pulled something to the ear and there was a speaker and some sort of a lever that you turned around. And then you got to talk to a switchboard operator, because these lines were actually physically connected to every house. I mean, today also, but unless you're doing the cellular telephony. But the landlines were still, in those times, they were connected to each house. But if you're calling from another city, you came to the city, you got the switchboard operator, and there was a lady sitting there, and she got the phone call, and you say who you want to talk to. And she had these jacks of all the people in town, and she would take and connect the line that came from outside to the line that you want to speak to, and then you talk to to the person you wanted to talk to. And if it was people within the town, then she would connect the caller to the person whom he's calling with these lines. So you have these switchboard operators that actually connected people according to who they wanted to talk to. Of course, today we don't talk to an operator, and all these switchboards are electronic. But these switches, the programs of the switches are huge. They are millions of lines of codes, these programs, for making the connections. And not only are they millions of lines of code, but because people don't really want anymore to sit there and wait 5 minutes until you're connected, so these programs need to work extremely fast. Because they need to work extremely fast, they still do it the old-fashioned way. There is no context switching. And if you need to do something 10 times, then you don't do a for loop, because in a for loop, you waste time every time updating, incrementing a counter, and checking if it's got to the top, and then going. So you have 3 or 4 operations that you're wasting for every time that you do the loop. And if the loop is 3 or 4 operations in itself, then at this point, you're doubling your time. That's unacceptable. So what they actually do is they copy the same code again and again and again, 10 times, 20 times, 100 times, if that's how much it wants to go. They copy it, except that the constant is changed in every time if there needs to be a different constant changed. But the same code is copied. They also don't do, in telephone switches, they also don't do calls, procedure calls, because in a procedure call, obviously you have to save you have to save the context, and then you go to the parameters, and then when you come out, you unsave it. No, you can't do that. So if something needs to be done in 50 different places in your program, you're going to copy the code as it is and put there. So they have these massive codes, and they're very hard to maintain, because suppose that all of a sudden we want to make a change in this procedure, and 100 places or 1,000 places are using the same code. You now need to find that code. And if that code also appears in all kinds of loops, then you need to now change it in every one of the occurrences for the loop, because there's no loop. They just go sequentially. So here comes a big problem, because, okay, so you'll say, well, the code is the same. It's the same, except the parameter is not the same. Here it's 1, here it's 2, here it's 3, here it's 4. Or here it's I, here it's j. So you have the same code. The names of some of the parameters has changed. And so you can't exactly do KMP and look for the exact match, because it's not there. They have parts of it are parameterized. The parameters change. And so how do you do that? So this was Brenda Baker's problem. She says, how do I do pattern matching? But when part of the alphabet is parameterized, in other words, it changes. So let's see how she defined it. Okay, so let me say also something else. In her case, she actually did the work with two types of alphabets. An alphabet that doesn't change, and then the parameterized alphabet. Now, when Martin Farage and Mutu and I came to look at it, we said, let's concentrate on the parameterized alphabet, because the other alphabet we know how to deal with. So you can do exact matching with don't cares, for example. The don't cares being the parameterized part. And then what you need to find is only the parameterized things. So, so in short, we actually simplified and we said, let's assume that everything is parameterized, that we don't have a fixed alphabet. But in fact, what we're looking for is the following. We have two strings. The light. We have two strings, S and T. And let's say that sigma S is the alphabet of S, and sigma T is the alphabet of T. And we say that S parameterized matches T if there is a bijection on the alphabet, so that if we take the string and operate the bijection on it, the string S, we're going to get T. So let's look at an example here. We have ABA, BB, and we have XY, XYY. Now, clearly, these things are very different. However, if the alphabet of S is A and B, the alphabet of T is X and Y. So if we take a function and we send A to X and B to Y in the alphabet, at that point, if we take pi and give it as an input S, what's going to come out is T. So at that point, we say that they parameterize match. Now, back to the context of Baker, think of these as the parameterized part. So these are parameters. In other words, if you have a part of a program and you copy that part somewhere else, but you just change the names of the parameters from I to J, from A to B, from X to Y, then this is the parameter part. That's what changes. Because for the program to be the same, they have to be changed consistently. Everywhere where there was an A in one of them, there has to be an X in the other. And when there was a B in one of them, there has to be a Y in the other. So the function has to be a bijection. It has to be one-to-one. It has to be onto. So it has to actually be a bijection between one set and the other of the parameters. But at that point, they parameterize match. There are other uses for this. For example, suppose you have an image in the computer. Now, many people want to copyright their images, and so then they scan all over the web. If their image appears somewhere, then they send a lawyer saying, you plagiarized my image, pay money. Now, so what happens if someone doesn't want the person to find his image? So what can you do? You can take the color map and just change a color map by one move a tiny bit. A human being isn't going to see the difference, but now everything is different. So everywhere that was dark red is going to be medium dark red. Now everything is changed, but it's a parameterized matching, because everywhere where there was a dark red, now is going to be medium dark red. Everywhere where there was a dark blue, it's going to be medium dark blue, whatever. So, so again, you have a parameterized match. Another place where this actually comes out, turns out to be very useful, is in not in pictures, but in plagiarism of code. So when I was at the University of Maryland, the TA came and said, I caught two people who copied each other because they have the same code. So I looked at it. Yeah, it was exactly the same code. So it went to a, they had there some honors tribunals for academic dishonesty that was composed of a faculty member and a student member and all kinds of things like that. So but the tribunal was not computer scientists. They were from all kinds of things. And they looked and they said, but it's not the same. Look, here it's I, here it's J. And so it's not exactly the same. They were smart enough that whoever copied obviously changed the names of the parameters. So the tribunal said it's not the same. Well, there actually are a bunch of universities, and some of it is even free. You can take it on the web. All kinds of packages that, if you feed all the student assignments, they actually detect plagiarism, who copied from whom. And some of the stuff that they look at is parameterized matching. So all of these are reasons to study the problem. Actually, you will be surprised at the end how we nabbed these guys, because we couldn't explain to them that changing the parameters is meaningless as far as copying from each other. But the way we eventually proved it was by the indentation, because the indentation there for loops and whiles and stuff like that, sometimes it was 3, sometimes 4, and sometimes 5. But it was, so within a program, sometimes it was 3, sometimes 4, sometimes 5. But between the two copies, the indentation was always the same. Where it was 3 here, it was 3 here. Where it was 4, it was 4. And where it was 5, it was 5. So I computed for them what are the chances that if you do at random this number of indentations and you choose at random 3, 4, or 5, what is the chance that you'll hit it exactly the same way? And they agreed that these chances are not realistic, and therefore it wasn't that they each did it separately and just happened to have exactly the same indentation. So that's how we nabbed those guys. But the truth is that they should have been nabbed even by the parameterized matching. Okay, so we're now forgetting the fixed part of the alphabet. Let's just think that everything is parameterized. In other words, like we defined here. We have string A, we have string B. They parameterized match if you can have a bijection on the alphabet that copies it. So if A is actually mapped to X, then all the A's have to be mapped to X. And if B is mapped to Y, then all the B's have to be mapped to Y. And if A is not equal to B, then X is not equal to Y. So it has to be a bijection. So is this definition clear? Yes. Mm-hmm. Okay, well, in her case, she looked at the entire variable as the alphabet letter. So you have to map the entire variable to, so if you have yes, the keyword would be a letter. Yes, but that's the difference. That's always the difference between real life and between an algorithm. So when you write an algorithm, you say, okay, This is my alphabet. This is my definition. I don't have the fixed part. In her case, what she actually did was every word, because in a programming language, you look at words. You have both the words that are part of the program and the words that are part of the program, like for, while, all of these are those. Every such word was a fixed letter in her alphabet, in her fixed alphabet. And then there were the words that are names, and every such name was a letter in the alphabet. So in my case, I'm forgetting the nonsense and just looking at the essence. And the essence says, I consider that one letter in the alphabet. So the entire word. Yes, that's also something. You live in theory too long and you tend to ignore these things. You say, well, the world is nice. There's an alphabet. I don't care how I get it. All right, so now back to pattern matching. Remember how we do pattern matching? The input is a text T and a pattern P. The text T is of length n and the pattern P is of length m. So that's our input. Now the output is all the text locations I, such that pi of p is equal to ti plus m minus 1, where pi is a alphabet bijection of these m symbols. In other words, we want to find all the locations in the text where the pattern parameterized matches. So now it seems like we have a bit of a problem, because everything that we did up until now, K and P, all these things, A is equal to A, but here if A is equal to B, that may be okay if B wasn't used before, and if it's and if everywhere in the future where I'm going to have A, I'm going to see B in front of it. So it kind of complicates things, and the question is, how well can we do it? However, knowing what we know, we say to ourselves right now that if I have a string S, there are many of them here, so some of them for sure I'm going to take 3, and one of them has to be good. So if I have S, excellent, and I have T, and I have Q. Because we're talking here about bijections of the alphabet, so if S parameterized matches T, and if the string, if the string S parameterized matches the string T, and if the string T parameterized matches the string Q, then the string S parameterized matches the string Q, because we have here alphabet bijections. So if every A here, every A matched to B, and if every B here matched to C, then obviously every A is going to match a C. They're not going to be all of a sudden two A's that match the same number because of the alphabet bijection. So since we have transitivity, so we have hope. We say, maybe we can use KMP. And in fact, we can. In this particular case, we're going to need to see how to do it. But in this particular case, we can use KMP as is. We just need to change the compare subroutine and then use the Knuth-Morris-Pratt algorithm as it is. We construct the automaton, we do the text searching, everything the same, except every time when you say is A equal to B, you basically go to this compare A, B subroutine that we're going to now define, and then run everything the way it is because of the transitivity that we have. Okay, so some history of the parameterized matching. So as I said, it was introduced by Brenda Baker in 1993, and there was a lot of work done both by Baker on indexing and by us. This is what I'm going to show you now. Then there was work that was done in two-dimensional parameterized matching. We're going to see today also how it was used in scaled matching. Some people dealt with the periodicity of the parameterized matching, because so you define what does it mean for a parameterized string to be to be periodic. Then there was work that was done about approximate parameterized matching. And what is not written here, but we're also going to see today, what about parameterized matching with don't cares? Because there you already don't have, you don't use the KMP for the don't cares. We use the fast Fourier transform. But for using the fast Fourier transform, when all these things change, how is that going to work? So, so the three things that we're going to see today is the vanilla parameterized matching, the algorithm for straight parameterized matching. We're going to see how this is used for scaled matching, and we're going to see parameterized matching with don't cares, because that gives us an opportunity, a final opportunity to really work with the FFTs, tour de force of work with the FFTs. Okay, so for the algorithm to work, we just need an alternate definition. And this definition is going to be the following. So you have to realize that when there's an alphabet bijection between S and T, it means that every A in the alphabet is exchanged by B, and no two A's are exchanged by the same letter in the text, and no same letter in the text has two sources in the pattern. So that's what a bijection means. But the bijection, as far as we're concerned, from an operational point of view, when can we say, now, if I am looking at a particular element, now I'm not looking at the whole string, but I'm looking at one element, SI. When can I say that SI parameterized matches TI? Well, the way that I can say it is the following. So I'm going to say that SI parameterized matches TI if one of the two things holds. One, if SI is not equal to all the K's up until I, so SI in the string S, this is the first occurrence of this letter, and it's also the first occurrence in T. So if it's the first occurrence of this particular letter in S or in T, then obviously they parameterize match. So if I'm going from left to right, like I'm doing K and P, I will say, okay, this is a match, since they don't appear before. And then I also, the next thing is, so this is if it occurs for the first time. But if it doesn't occur for the first time, so in other words, it has occurred before. Well, if it has occurred before, then all the K's from 1 to I minus 1 until here, SI has to be equal to SK, if and only if TI is equal to TK. So I will still say that SI is equal to TI if all the locations where SI occurred before, there was a TI there. And all the locations where the TI occurred before, there was an SI. So that, then I can say that they're the same. So if I'm going from left to right and I'm actually comparing, I will say, okay, SI is equal to TI if and only if A, it's the first time that they occur, or every time that there was an S, there was a T, every time there was a T, there was an S. So every time that this symbol occurred in S and T were exactly the same indices. So at that point, they match. Yes. Of course, that you don't really need to check it for all pairs. You can actually check it for the last one, just for the last time, and assume if you really go from left to right, so inductively you assume that all the others were okay. So yes, that's a good point, and when coming to implement this, then obviously we can do it. So you can say, all right, I am A, the text is B. The last time that there was that there was an A was also the last time that there was a B. And the other one, and inductively, I mean, then already we checked. Either they were the first time, or if they weren't, they checked what happened before. So I trust that. Okay. So here's the parameterized matching algorithm. We're just going to run KMP as is. But the modification we're going to do is the following. first we're going to need to construct some table. We call it the table A, where our AI is the largest k less than I, such that pi is equal to pk, if such exists. And if not, we just put I. So what does that table tell us? It basically just tells us, is it the first time that I see the letter in index I, or have I seen it before? And if I've seen it before, then that tells me what is the index of the last time I saw it, which exactly is going to put to use what you suggested me about just checking the last time. So I know where to go in order to check it. And the second thing that we need to do is use that in order to replace the equality checks. Because when I'm checking whether a pattern symbol is equal to a text symbol, I'm not really checking if the symbol is equal to it. So when I say, is pi equal to tj? In KMP, this happened all the time. Is pi equal to tj? Well, fine. Everywhere where KMP says pi equals to tj, go to this subroutine that says compare pi to tj. And how do we compare it? Okay, if ai is equal to I, and tj is not equal to all of the symbols from j minus I plus 1 till j minus 1, that means that this is the first time that we see tj, and it's the first time that we see pi. At that point, they're equal. Now, of course, here, this thing is what we're going to have to say later, how do we do this fast? And here we can't pre-do it, pre-process it, because we don't know what distance to be pre-processed. In the pattern, it was easy. That A did it exactly because we know where we start. But in the text, you'll go back to where you are according to the pattern where you are at this point. So you need to actually do it for all starts of pattern. That would be m of them. You obviously can't pre-process it. So how do we do this fast? We're going to see. But if this happens, then we return equal. If this is not the case, in other words, ai is not equal to I, so ai is not equal to I, and if tj is equal to tj minus I plus ai, so tj, ai is not equal, it means that this symbol occurred before. So let's see what's the story with tj. So this is the index relative to where we are in the text, where in the pattern this symbol appeared before. So check if they were the same. So we assume that everything parameterized matches up to here. Now we're checking this new one if it parameterized matches. So if the last time that the pattern occurred was also the last time in the text, or they match, then there is a parameterized matching. Let me draw this. And again, we have we're basing ourselves on the induction here and saying, suppose that we have an A, and this is the text, so we have the text here, and we have the pattern. Now we check the pattern all the way up to here, and it parameterized matched. And now we have a B in the pattern. There's an A in the text. Is a B equal to an A? Does the B parameterized match the A? Well, again, if it was the first time that B appeared, and in this entire area there was no A, then they match. Because in parameterized matching, this is the first time they appear. So that's what the bijection is going to map. But if the B actually appeared before, so the last time there was a B was here, go and check if there was an A in the text in that particular location. And if there was, you return that they're equal. And if not, you return that they're not equal. Now, Yes? Two patterns. Oh, yes. It doesn't, yes. So you can say there is a parameterized matching here and a parameterized matching there, and it's a different alphabet bijection. That's okay. That's okay, because all we want to do from a theory, it wouldn't happen obviously in the case of Baker, or even it could, but because it could. But the point is, the way it's defined, yes, we defined it as uh, if there is a bijection from the pattern to the text in this M, in this area of M elements, then I'm going to declare a match. So, for example, if you have the pattern, 1, 2, 3, and if you have the text 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then there's going to be a parameterized match in every location, because 1, 2, 3 obviously is 1, 2, 3, 2, 3, 4 is 1 mapped to 2, 2 to 3, 3 to 4, and so on, because they're all different here and they're all different there. So every location will be a match, even if they even if they overlap. That answers your question? Okay. So let me go back and repeat the part that there was no battery. So why do we say that it's enough to check in this check that if AI is not equal to I, it means that this was the last time that we saw a B. TJ, so we go to whatever it was in this particular offset, and if it's an A and it's equal to this A, so if TJ is equal to what's in the text in this particular offset, then we say it's a match. And the question was, why can we say it's a match? Maybe there was another A here that was a C, and then it's not a match. But the point is that this could not happen, because then you have an A matching a B and an A matching a C, and even up to here we're not going to have a parameterized match. And our assumption is that everything parameterized matches up to here, and then we go on. So that's why this is well defined and as an equality. And if we do that in the Knuth, Morris, and Pratt, then we can continue as long as there's a parameterized match. And then when it doesn't match, we go by the failure function and we move. But when we move things forward, it means that we looked for the longest prefix that parameterized matches the suffix in the pattern, and because of this parameterized matching transitivity, that actually would be the longest prefix that parameterized matches a suffix in the text. So that would work out, except for one thing that we still need to say, and that is, when we construct the automaton, we also do comparisons. Because remember, as you go to the back, you say, let me remind you how we constructed the automaton. In KMP, we said that we go to the back here, and if this symbol, let's call it A, is equal to A, then this is going to be the back arrow. And if it's not, then you'll go one more to the back. Now, in our case, the question is not if this is equal to A, but the question is, does it parameterize match to A? So what we want to find out is whether, if this was a B and this is an A, if the B that came before it parameterized match the A that came before it. So that's our question. And so we need to Okay, you understand what is the difficulty here. So we need to define a compare of the pattern and the pattern. This is a compare of a pattern in the text when we do the search. But we also need a different algorithm for comparing a pattern and a pattern. So when we do is pi is equal to pj, instead, when the KMP pattern construction algorithm does is pi equal to pj, then we're actually going to go to this compare algorithm and ask the question. And so what are we going to say? Well, here it's a tad different from what it was before. So here we say, if ai is equal to I, in other words, if this is the first time in the pattern that we see I, and if pj is not equal to all the p's that came before, then we return equal. That's good. But the thing is, it may be that we've seen I before, but it was too far. Okay, so the B that occurred before is further than the shift. So this is really the first time that A occurs in this particular area, and the B appears before, but not in that length. So how are we going to take, so in that case, the B is also in some sense, it's the first time that it's appearing. So we need to account for that. So if AI is equal to I, or if I minus AI is greater than or equal to J, so if the J itself, the part of the J that we're looking at, is too small, so it's true that AI appeared before, but it appeared too far for the smaller of the two, then it's really as if it's the first time that it's appearing, because I'm not counting what happened before that. So actually, it's the opposite of what I drew for you, because the the B, okay, the prefix occurs all the way to the end, but this suffix doesn't occur. So it could be that here there's an A, so A has occurred before, but since we're shifting it, then it's the first time in this particular part. So that is that's the smaller of the two that we need to compare. Okay, so if one of them, so if the longer one appears for the first time, if the shorter one appears for the first time, and in the longer one, it may have appeared, but in an irrelevant situation, then it's still, you can return equal, because as far as we're concerned, we can do the shift. This is still a parameterized match. It's the first time that they both appear. But if I minus AI is less than J, and also Pj is equal to P, J minus I plus AI, in other words, they both appear before within the prescribed area, and they were the same letter before, at that point, you can also return equal. So everything parameterized matched until now, it's going to parameterize match from now on also. So these are the two subroutines that we need to change. And as far as the correctness, the automaton construction correctness guarantees here also the failure arrow is going to point to the largest prefix that parameterized matches the suffix. And because of the transitivity, this is going to work. We can do the search, and KMP works wonderfully. So the only thing is the time, because KMP is linear time. But we have a new compare subroutine. And in the compare subroutine, everything seemed to be O of 1, except for the part where we have to go back and search if it's the first time that I'm appearing from the beginning, in the text, from the location minus I until now. So what we're going to do is the following. First of all, we can always take the text size to be less than or equal to 2m, and we've seen that last week for the FFT, but once we know how to do this trick, we can always do it. You can always assume that the text is not huge, but it's twice as much as the pattern, because if that isn't the case, remember you chop it into blocks, into overlapping blocks of 2m, and then just look at the 2m. So we can assume that the text is of size less than or equal to 2m. And so the compare is going to take time O of log sigma, where small sigma is the minimum of the alphabet size and the m. So if so because ym, because we're not going to have more than m symbols in the text and the pattern altogether, and the alphabet size, because that's the alphabet size. So when we want to actually find out to search whether TJ or PJ appears before, well, you have what appeared before in a balanced tree, in a balanced search tree. It takes logarithmic time to search for this particular letter in the search tree. And if you find it, look at the index where it's at, and is it good enough for me or not? I mean, is it far enough, and I am saying this is my first time? Or is it close, and then I'm saying not equal? So there's going to be a logarithmic degradation, log sigma. And the question is going to be, can we actually do it in linear time, like real K and P, or are we destined to live with this log sigma? Well, if you have an alphabet that is fixed, then this log sigma is going to be O of 1. Then that's, well, we're going to see that. But in general, the alphabet size, if the text is of length 2m and the pattern is of length m, the alphabet can't be more than 3m. So you build your 3m binary search tree, balanced search tree, and then your favorite 1, 2, 3 tree, red, black, AVL, and in logarithmic time, you'll find it. Yes. So the automaton construction is then going to be O of m log m, and the m log sigma, and the text scanning is O of n log sigma, where sigma is never worse than m. So because if we chop the text and the pattern to these small sizes, then that's what bounds it. And the question, of course, is can we do better? Okay, so we would expect that if the alphabet is 1 through n, for example, we should be able to do better. And we are. We can do that in completely linear time. Why? Because we can construct an array of size n. We go linear time, we pass through the text and the pattern, we construct an array of size n, and as we go through the text and the pattern, start with the text, let's say, and then the pattern. So you go through the list of all the indices of the symbol 1. So you see a symbol 1, you put it in this list. You see 1 again, you put it here. You connect it to the list. So at the end, you're going to have the list of all the locations where you have the index 1. Then you have the list of all those that are in index 2 and so on. The time to do that, of course, is going to be linear because there's n lists, that's your alphabet, and you do a random access to the pointers to the list. So if I see number 4, I know what the list is, and at that point I have the pointer to the end of the list, so I can put the new element there, and it's O of 1 to construct it. So in linear time, we can construct these lists, but once they're constructed, if you want to check if Tj is not equal to Tk for these particular k's, then, and assume that the symbol that was in Tj is A, okay, so you have A pointing to, you go to the list of the A. You do it, as you construct the lists, keep a double pointer from the list to the element that came there. So you have in Tj, you have an A. It points exactly to its location in the list. So you check if the previous index to J in A's list, that was exactly the one before, okay? Is that less than J minus I plus 1 or not? So in O of 1, you can actually check that. For here, you don't need a balanced tree. So that's for a fixed alphabet, and we're happy that we can do it for a fixed alphabet. But what happens about general alphabets? And the sad news is that we can't get rid of the log, but we'll prove that we can't get rid of the log. So we're going to show a lower bound, and we'll do it in the, at least in the comparison model, because we're all doing here comparisons. We're not assuming anything on the alphabet. and therefore we are in the comparison model. Now, the element distinctness problem is the following. Suppose you have an array, A1 through AN, of natural numbers, and I want you to decide if all the elements of A are distinct. So in other words, no element repeats. So you have an array, no elements repeats. So how can you do that? How fast can you decide that thing? So what do we know for the element distinctness problem? We know that in the comparison model, for general alphabets, you have a lower bound of n log n. You can't do it faster than that. It's kind of like sorting. And we know that for alphabets 1 through n, in fact, any alphabet that's a polynomial of n. So if you fix a polynomial, you can always do that because you radix sort them, and then you can rename it 1 through n. So in linear time, you can change it to 1 through n. For those alphabets, we can do it in linear time. And the way that you do it in linear time is exactly how I showed it before, because you can construct this list of indices. And as soon as you see that you're trying to put the same element in the same list, you know that you are not distinct. If you finished and you never tried to put two elements in the same list, then you are distinct. So the element distinctness problem can be done in linear time if the alphabet is 1 through n, and it can't be done in linear time otherwise. So it's proven that it has a lower bound n log n. So all we need to do in order to show that we can't really do parameterized matching for general alphabets in linear time is to have a linear reduction from the element distinctness problem to parameterized matching. Because if you linearly reduce the element distinctness problem to parameterized matching, and if you can parameterize match in linear time, then you have two linear operations here. It means that you actually can solve the element distinctness problem in linear time. And we know that that can't be done. So such a reduction is going to automatically give us a lower bound on the element distinctness problem. Yes? I have to move away from the air conditioner, yes. What's the definition of EDP? EDP means you are given an array. You are given an array A of numbers. 5, 7, 10, 3, 1, 11, 24, 100, okay? You're given an array of numbers. You have to decide whether any number repeats twice. So here, every element is distinct because it appears only once. But if I also add here, let's say 10, then there's no element distinctness because 10 appears twice. So this problem is known to have in the comparison model, a lower bound of n log n. You really need to use logarithmic time if your numbers are not 1 through n. So if you have a general alphabet, all kinds of numbers, then there's no helping for it. You kind of need to sort it in order to find out. Okay, so let's now see the linear reduction. Let's assume that A1 through AN is our array of numbers. And what we need to do is, in linear time, produce an instance of the parameterized matching, so that if we say yes to the parameterized match, then there is an element distinctness, and if not, not. Okay, so what we're going to do is, the first thing is, in linear time, we're going to check if A1 is unique. Now, that's easy, because take A1, compare it to A2, to A3, to A4, to A5, to A6. If at any point you see that it's the same, then you say, okay, I don't even need any reduction here because I already know that I am not distinct. But if you go all the way to the end and A is not equal to anyone, then at least you know that A1 is distinct. So that we can do in linear time. And if it is distinct, what you're going to do now is construct a string S that is A2 to AN and A1 at the end. So basically, you just shift rotate to the left, one to the left. So the one goes to the end, everybody gets shifted. Now, we're going to say the following. A parameterized matches S if and only if all the elements of A are distinct. Okay, so do your parameterized matching, and suppose you could do it in linear time. Well, and you find out that they parameterized match, then you know, you come back and say, okay, in linear time, I just proved that A, all the elements are distinct. And the other side also holds true, because if it doesn't parameterize match, then you know that not all elements of A are distinct. So in any reduction, you need the if and only if. So one direction is trivial, because obviously, if all the elements are distinct, then it doesn't matter how I shift rotate or any permutation I take, I'm going to get a parameterized matching, because all the numbers are different, so it parameterized matches. So this direction is totally trivial. We don't even need to talk about it. The second direction is the direction we need to talk about. And that's the one that, suppose that we have a parameterized matching, how do we know that all the elements are distinct? Okay, and so we're going to do this by induction on the prefixes of A. So we're going to show that every prefix of A is parameterized matches the, that every prefix of A has element distinctness. And if every prefix of A has element distinctness for all prefixes, it includes A itself. So all the elements are distinct. Okay, so let's start. A1 is unique. We checked. So A1 never appears. And when I say that every prefix of A has element distinctness, it means that every element in every prefix of A only appears once in entire A. That is the induction that we're saying. Okay, so if for every prefix, every element only appears once, then obviously when we end, everything's good. So A1 is unique. We checked that. It only appears once. So the base of the induction works. Now, let's assume that A1 through AK are distinct. So, what do we mean that A1 and AK are distinct? It means that AK is unique in particular. I mean, all of them are unique because that's our inductive assumption that all of them are unique. In particular, AK only appears once in the entire A. So that's our inductive hypothesis. But if AK only appears once in the entire A, and AK was actually parameterized match to SK, because we had a parameterized matching. So what that means is that SK also only appears once in the entire array, because you cannot have something that parameterized matches. If it appears only once, then because of the bijection, whatever is matched to also has to appear only once. It can't appear more than once. So if AK appears only once, then SK that it matches to appears only once. But what was SK? Remember, we shift rotated. So SK was really AK plus 1. So AK plus 1 also appears only once, so AK plus 1 is unique. So that means now by induction that all the numbers are unique. So that's the direction that was a little bit harder to, that was a little bit more than trivial. So again, let me draw the whole thing in case it's not entirely clear to someone. So we have A. So we have A1, A2, A3, etc. And then we have S. And S is A2, A3, A4, etc. Okay, so if we assume that so we have a parameterized matching, and if we assume that A3 is unique, so A3 only appears once in the entire array. Now, A3 is matched to A4. So whatever is written in A4 cannot appear more than once because they parameterize match. And therefore, we now know that A4 is unique. But if A4 is unique, because it parameterized matches A5, then it means that A5 is unique. And so on. A5 matches A6, and you go on all the way to the end. All we needed to do was to make sure, though, that A1 was unique, because but that's the basis of the induction. But we checked that, and we did that in linear time. So that we can do. So we conclude from this that parameterized matching can be done using KMP in linear time, but for infinite alphabets, you do have a logarithmic degradation. You cannot do it in strictly linear time, because if you could have done element distinctness in strictly linear time, and that we know you can't do.